Okay, Lab 1, Activity 1. You have 3 different configurations of charges, and you have a flux detector, a cylindrical or spherical flux detector. When you use it to surround the charge, it measures the net flux through the detector. So if there's no charge, there's no flux. And if you enclose the charge, if you see a positive flux, you know you have a positive charge inside. If you see a negative flux, you know you have a negative charge inside. And the amount of flux is proportional to the charge inside. That's Gauss's law, right? And just to remind you, you have 2 relationships that we're using for all these exercises. The first is the definition of flux, which for the most general case has to be an integral of E dot dA, a dot product, E dA cosine theta. A should be a vector. And in the simple case, the one we use the most is just the magnitude of the field times the magnitude of the area times the cosine of the angle between them when these quantities are all constant. The definition of flux. Okay, the relationship between flux through a closed surface and what's inside the surface. So the amount of flux through a closed surface is always proportional to the charge inside. In fact, it's equal to the charge inside divided by epsilon naught. So if you know the charge inside, you can calculate the flux. If you know the flux, you can calculate the charge inside. So in this exercise, you're getting the flux through the detector, so from that you can calculate, using this equation, the charge inside. So I don't think there's much more to say. You just put the detector around the charges and you find the flux. It reads the flux. So from that you can calculate exactly the charge inside, or you can rank the charges inside, right? They're going to rank according to the amount of flux enclosed by the detector. Okay, I think this is pretty straightforward. Okay, number 2. Notice I'm skipping 12. 12 should be at the end. I can't move it right now in Moodle, but it should be, you can do that one last. So here's number 2. It's very similar. These are lines of charge, so in order to enclose them, you have a cylindrical detector. Only the difference here is the detector can't enclose one charge. It can enclose in 2 or it can enclose 3. But it can't enclose 1. So you're going to have to do some sampling and use some algebraic logic to figure out the flux through each one individually. You cannot measure it directly. You're going to have to calculate it from measurements. And I urge you to do that on your own. But if you're really stuck, I am going to give you a trick in a minute, but try to do it on your own first. Okay, here's the trick. Notice if you surround A and B, there's 0. So that tells you something. I'm not going to tell you, but it tells you something. There's 0 flux. There has to be, what? A net charge of 0 inside. And yet if you slide the detector to include all 3, now the net flux is not 0. There's the answer. I'm not going to go any further. And if you surround C and D, it's 0, but if you surround C, D, and E, it's not 0. So I hope that hint is good enough that you can solve the problem if you weren't able to. Okay, here's number 3. Read the warning. This messes people up every time. The display of colored arrows is distracting, even deceiving. So I urge you to ignore that. See the thing like a blank screen. It'll lead you the wrong way. And what you have is you have a flux detector, and you can wander around the space. And what does the flux detector do? It tells you the flux through the detector. And what does the flux through the detector tell you? It tells you the amount of charge inside the detector. But the question is charge density. Well, density is mass density is mass per unit volume. So charge density will be charge per unit volume. It'll be coulombs per meter cubed. And we should think of it tells so that since the volume of the detector is constant, the charge inside will be proportional to the density wherever you put the detector. Make sure you understand that. So wherever you put the detector, you can move it around anywhere in the area that's displayed, the big square. Of course, we're thinking of it as three-dimensional, but for us it's only two-dimensional. And so investigate, right? The charge density will be the charge inside divided by the volume, but the volume's constant, so the density will be proportional to the amount of charge inside. So wander around the space, get a feeling for mapping out the charge density, right? You want to map it out and do that. Just do that. See what you come up with. And then you can come back and check. I'll give you a little more information. I don't want to tell you the answer, but come back after you've done it and see what you came up with compared to what I come up with. Okay, here's what I come up with. When I go to the center, it's 0. As I leave the center, it stays 0 in a pretty big area, right? And I've got to get pretty far from the center before there's any charge inside the detector. And the more I go away from the center, what happens to the amount of charge in the detector? It gets bigger and bigger and bigger. In fact, we could investigate. If I go, say, and you can see, you can get your x and y position. If I go to, like, say, y equals 0 and x equals 2, I don't want to take the time to do that, and then go to y equals 0, x equals 4. So be qualitative and quantitative in your investigation and get some detail. And then what happens if you go along the y-axis? What happens if you go along the negative x-axis? What happens if you go along the diagonals? These are all things that you should explore, and by exploring that, you should be able to come up with a picture. You should be able to describe or sketch out a picture of what the charge density would look like in this square or cubic area. Okay, number 4, another exercise in mapping out using flux detectors the charge distribution of charge in an area, right? And we map that out by charge density like we did in the last one. And in this case, we have, rather than one detector, we have a small square detector or cubic detector. We have a small circular detector like the last one. We have a larger circular detector, and then we have a very large circular detector. So each one of these is useful in its own way. The smallest detector will give us the finest detail, and the largest detector will give you a sense of the overall distribution information that would be hard to get with the small one. So think about how best to use all 3 detectors to map out the charge density in this square region. And remember, the gray circle is just a reference circle. It is not an object. The instructions tell you that. And once again, this is a lab exercise, so do as much as you can before. I don't want to leave you hanging, so I'm going to give you a few hints and a few comments, but I urge you to do as much as you can. You're honing your investigative skills, your skills at observation, and your cleverness at using the 4 detectors. So do as much as you can before you check in with what I'm going to do. So I think there's no one way to do this, but I would start with the smallest detector and just wander around to get the detail. You see, oh, like 0, I'm seeing 0. So all around the outside there's 0. How about like outside the gray sphere, it seems to all be 0. Once I go inside, oh, well, even inside the gray sphere there's 0. But, oh, here's a place of red. And here's a place of blue, and it varies quite rapidly, right? So what's the shape of that red? Where is the red located? Where is the blue located? And how does the charge density change by position? Because you can get the positions, right? So where it's 0, a lot of it's 0. Not much red, and it changes very rapidly, and the blue gets really very strong. Remember, the charge in the flux is proportional to the charge inside, and the charge inside would be the charge divided by the area or volume of the object. Okay, so after I've gotten as much information as I think I can with that narrow detector, I'm going to pick up the larger detector and just see if that helps me to gain any information. And I'm looking at the numbers and the positions. And one of the things I'm noticing is I can't get as big a reading. So what does that tell me? Okay, but am I seeing the same shape, the same distribution? Yeah, I am. Let's go to the bigger detector. Okay, now this encloses more area. So notice, interesting. Where do I just get red? Here I get blue. What if I put it at the center? I'm just getting a little bit of blue. As I go this way, the blue gets bigger. Actually gets quite large there. How do we explain that? That's a little puzzling. I'm not sure if I even know the answer to that, but it's worth thinking about. Then let's go to the biggest one. And what does that tell us? That tells us if I surround the whole gray sphere, I'm getting a flux of -1, basically almost 0. Let's go back to the other detector and put it on center. -10. Is that consistent with the other information we found? So there's really quite a bit of thought and investigation you can put into this. And what I would guess for this is that there's still some red charge. Where did we find the red charge? Since this has more blue, there must still be some red charge outside that green detector. Why? Because when I go to the blue detector, I essentially get 0. And so what does that mean? Well, even though the blue was so intense in some places, it means that the net amount of blue charge is what compared to the net amount of red charge? I would never have guessed that if I didn't have this large detector. So anyway, those are all ways of getting information and answering the questions in the lab. Okay, number 5, you're calculating the flux through, actually the flux into and out of each of these three spheres, the red, the green, and the blue sphere, different sizes. And so to calculate flux, what are you going to use? Well, you don't have any information about the charge inside. Then you would use Gauss's law, but you do have a red dot that you can drag around and read the electric field. So in that case, what you want to use to do this is the equation for calculating electric flux. So just to remind you, this is Gauss's law, the relationship between flux through, closed surface and the charge inside. And these are closed surfaces, but we don't have any information about the charge inside, so we go to our definition of electric flux, which in the most general case is an integral, but in a special case of where EA and the angle between them don't vary, we can use EA cosine theta. So how are we going to do this one? Actually, there's two, right? There were two configurations. Same shapes, but different field. All right, so if we take our field detector and we drag it around, what do we find out? We find out that the field is uniform everywhere. Now notice this is the magnitude of the field, but what's the direction? The direction is given by the arrows. So for each of these spheres, the flux that goes in is the flux that comes out, because the field is uniform. Only we have a problem. The field entering enters over a semisphere and hits the surface at different angles for every piece of surface. So to do this, we would have to do an integral, and obviously whatever goes in has to come out, so we wouldn't have to do it twice. But there's a trick. We're not going to do that integral. What we're going to do is we're going to cut the sphere in half. And when we cut a sphere in half, what do you have? You have a circle. And so any flux that enters through this half a sphere, semisphere, has to pass through this circle. And the field passing through the circle is, in fact, normal to the surface of the circle. So in that case, we can just use EA cosine theta, because E is uniform. The angle will be, remember, not 90, it's going to be 0 degrees because it's normal to the surface. And the area will be the area of the circle. So how do you get the area of the circle? You need to take your cursor, measure the diameter, and then calculate the area of any circle, pi r squared. And that way you can get the flux in and the flux out of any of those spheres. Oh yes, there is configuration 2. And what's different about configuration 2 is, the field value is different and the direction is different. But you should see that as you drag it around, what you find, it's actually not much different from configuration 1. So just do the same thing you did there. Okay, another one, similar, only here we have two configurations, and they both involve a green box. So much like the last one, only instead of a sphere, we have a box, and that makes it much easier, right? Because the surfaces are flat, and you have your field detector, and like before, you can drag the field detector around. You see now the field is reading at the bottom. It's also reading magnitude, so the direction is given by the arrows. And you can get the positions. You're also getting positions. So in this case, it should be obvious what to do. But just in case it's not obvious, you should notice that the field enters here, leaves here, so there's flux entering on the right, leaving on the left, and the top and bottom and the sides, the field is parallel to the surface, so it doesn't pass through the surface. And for configuration 2, notice the field looks the same, but it's not the same. And you have your field detector, so just notice the difference in these two fields and think carefully about what that means. Remember, if the flux into or out of a surface isn't zero, it means what by Gauss's law? It means that there's net charge inside the closed surface. And now, number 12, 2 animations. And so read over the instructions. When you start play, you'll have an expanding spherical surface, a flux detector. So watch what happens when I play animation 1. Press the button. There's the detector. It's expanding. As it expands, it's reading the flux through it, and it's plotting it in real time in the graph to the right. Notice what happens. The expanding detector. Now the flux is constant. Once it passes outside of the gray sphere, it's constant. What does that mean? If the flux is constant by Gauss's law, it means what? And then finally it stops at 10 seconds. Let's take another look at that. The detector starts. The amount of flux, it's increasing as the volume of the detector increases. The flux is increasing, and all the numbers for at each particular size, and then it becomes constant. And the maximum value that it reaches, 300 flux units, newtons. Oh, notice it's centimeters squared per coulomb, so be careful of that unit. And then if we go to animation 2, and we do the same thing, notice the different behavior. Okay, the flux detector is expanding, the flux is remaining where? At 0. 0, what does that mean? Gauss's law, if the flux through a sphere is 0, it keeps expanding, and when it hits the surface, it jumps to the value of 300, and then it stays constant. So think about that. And this is related to the assignment. There are 2 different situations, and you should be able to puzzle them out by this, by the behavior of the flux plotted over time for these 2 situations. And last but not least, the table of contents for the 7 lab items. I didn't do number 8. These are the times in the video where you'll find them if you're just looking for help on a specific one. Good luck!